The relationship between garbage collection and event emitters is one of the most important things to understand in Node.js. Since GC can only sweep objects that are unreferenced, event emitters will not be collected after you attach event listeners to them. Consider a simple echo server. You create a server, attach a connection handler, and start listening. GC will never collect that server object, which is correct, it's the main object of the program. But in other cases, your emitters won't get swept because of references to listeners. Most importantly, event callbacks are functions, and functions are extended objects in JavaScript. They won't get swept either. This becomes a problem when you use the adapter pattern to create an abstraction for each client connection. You make that abstraction an event emitter to decouple it from other parts of the application. While the client stays connected, any event listeners that don't explicitly unlisten will not get garbage collected even if they're supposed to be gone, even if you null them from the outside. And if your connection gets stuck and doesn't time out, a common scenario with mobile connections, you end up with zombie connections accumulating in memory. Now let's talk about referencing objects more carefully. The main goal of GC is to identify memory your application no longer uses, usually because your code no longer references it. When a function returns a local variable, that variable gets dereferenced. But what about another variable in the same function that gets returned? It doesn't get dereferenced until you explicitly release it. And even then, if you pass your object to do something and do something internally holds a reference to it, setting your local variable to null does nothing. There's no way to force another function to release a reference. The function can also create a circular reference by setting a property on the object that points back to itself. GC is clever enough to detect cycles when the rest of the application no longer uses the cycle, but the more complex your code, the harder it is for GC to reason about this. In V8, there are three primitive types: numbers, booleans, and strings. Numbers come in two forms. Small integers, or SMIs, are 31-bit signed integers. They're the fast path. When a number exceeds the 31-bit integer boundary or becomes a float, V8 represents it as a normal object, a double, or a number with extended properties. This is why staying within 31-bit integer range matters for performance. You stay on the fast SMI path. Strings also have two forms: strings inside the heap, and strings outside the heap with a wrapper object on the heap pointing to them. Arrays are objects with a magic length property. Native objects, like file handles or sockets, are not in the heap itself. They're wrapped like some strings and therefore not managed or swept by GC directly. Now, let's look at what GC actually does during a cycle. In each cycle, GC pauses V8 execution in what is called stop the world. It knows exactly where all objects are in memory and what references exist. If there are too many references, GC will process only part of the object heap, minimizing pause time. GC runs through three phases. First, traverse the graph from the root, marking every reachable object. Unreachable objects are left unmarked, shown in red. Second, sweep, free the memory of the unmarked objects, leaving gaps. Third, compact, move remaining objects together, eliminating the gaps. Before 2012, V8 used marksweep and markcompact, which processed entire zones at once and caused significant pauses in medium-sized applications. In 2012, Google introduced incremental marking. Instead of traversing the whole zone in one go, GC traverses part of it, making the pause smaller. Combined with lazy sweeping unreferenced objects only when memory is needed, not all at once, V8 can distribute the GC workload much more evenly. The result, more frequent but much smaller pauses instead of rare catastrophic ones.